morning, ladies and gentlemen. My name is Oliver Bolosan. I'm a senior in computer engineering. I am graduating in May 2017. I'll be attaining my computer engineering bachelor's degree along with a computer science minor.
All right.
So the review I am doing today is about the Slate X7. It is a MIPS processor created in the course CECS 440 Computer Architecture. So the purpose of this project was mainly for learning debugging, documentation, practicing our verbal skills and our written skills. I included a quote in here from Dr. Emmett Brown, who is in Back to the Future. Engineering is the art of modeling materials we do not wholly understand into shapes we cannot precisely analyze so as to withstand forces we cannot properly assess in such a way that the public has no reason to suspect the extent of our ignorance. I like the quote. It just kind of goes to show that engineering is all about learning and just about trying to explain exactly what we are designing and trying to invent. So millions of instructions per second, that is the MIPS processor. Ours is a 32-bit processor. It is reduced instruction set computing processor, therefore is a RISC machine, therefore it has fixed instruction lengths, load store instruction sets, limited number of addressing modes, and a limited number of operations. The other kind of processor that we have is a CISC machine, which is a complex instruction set computing processor. Those are typically Intel related, and that was a little bit of our focus this semester. However, we are looking at RISC. So the instruction set architecture, it allows the programmer to understand the architecture's composition by way of available registers. We have 32. The operable data types, in my processor I have 2. The different addressing modes to obtain the operands, the instructions to process and manipulate data, and the binary formats of the instructions. The Slate X7 is a Harvard memory architecture. This means that it has a physically separate storage and signal pathways for instructions and data. It's possible to access program's memory and data memory simultaneously, and it is a read-only, and the data and input-output memory are read and write. So as I said earlier, we have 32 registers, right? So it also contains a 32-bit address space, and the memory is structured such that it is byte addressable in big endian format, meaning that the big end of the data, the 32 bits, from bits 31 to 24, are in the lower address, and CD will be looking at, for example, at 3FC we have AD, 3FD will have CD, 3FE will have EF, and 3FF will have 00. There is also a little endian format, which is reversed. Obviously the little end will be at the lower address. However, we are big endian format. In the machine register set, we have 32 registers that are 32 bits wide. We have a 32-bit program counter, high and load, and 5-bit registers for flags and the interrupt enable. Flags are going to consist of carry, overflow, negative, and 0.
Now, is that an enhancement to the MIPS, having the five bits for those particular flags?
The enhancement that we have in the MIPS is the interrupt enable.
Mm-hmm.
This allows us to perform to allow interrupts to happen, whether they're external or internal, in the system.
Okay.
The data types that we have in the Slate X7, we have bits, obviously there's 0 and 1, the bit string, 4 bits, 8 bits for a byte, 16 bits for a half word, and our word is 32 bits. We do have 64 bits, a double word. Typically when we complete an instruction such as multiply or divide, multiply we get a 64-bit product. As for divide, we get a quotient remainder, which we split up amongst 32 bits each. That is what the high and low registers are for in the previous slide. Now we can handle 32-bit signed operations and 32-bit unsigned operations.
Right.
I'd just like to note that a future enhancement would be to add a floating data type. Was not able to do so at the current time, but I will look to enhance this processor. So the addressing modes I have available are immediate, register, and register indirect. Immediate, typically in this design, I have the immediate 16-bit immediate value located within the instruction format. In register, they're going to be your typical register to register operations, such as register 2 and register 3 are added together and put into register 1. Register indirect is a instance when a register is used as the base index, and we add a 16-bit immediate offset to the register, and that will be calculated as our effective address, in which we store a word into R9 located at the address R7 plus 12 times 36. So, as I said earlier, all instructions are 32 bits wide. We have 3 instruction formats. They are R-type, I-type, and J-type. R-type typically stands for the registers that we will be working on. I-type are the instructions that have immediate values, and J-type are the jumping instructions. So in R-type, the most significant bits, 31 to 26, are 0. That is what is a unique instruction format for R-types. So when you see a 0 in bits 31 to 26, you'll also have a function code in bits 5 to 0. This area is, in the instruction format, really is, that's what will tell you that, whether it's an add or a subtract instruction. As I said earlier, you have operations like add, R2 and R3, and store the result in R1. R2 will be sitting in the RS code between 25 to 21. RT will be R3, and that will be encoded into 20 to 16, and R1 will be encoded into 15 to 11. We also have a shift amount. We have bits for shift amount, where we can dictate how many bits to actually, or how many locations to shift our data. So say we have R5, and R5 would then, for this particular instruction, be encoded into RS. RT would be encoded into R4, R4 would be encoded into RT. We would not use RD in a shift instruction, and the shift amount would be the binary value 6. Next, we have our I-type instructions. The I-type instructions are when the immediate value is part of the instruction in bits 15 through 0. So we have a 16-bit immediate offset included in the instruction. So R2, it functions as, it is encoded in the RS field. R1 is encoded in the RT field. And the 16-bit immediate for the load upper immediate instruction is FA. Now, these I-type instruction formats also contain the branching instructions, where the branching location is within the 16-bit immediate value.
What's the second register on the Louis?
The second register,
Yeah, how's that Louis work? So I know it stands for load upper immediate, so you've got a 16-bit value that's loaded in a register. Which one?
it is loaded into R1.
What's R2 for?
I might have made a typo.
Yeah, you go back and look at that maybe. Yeah,
Yeah.
okay.
Uh-huh. So we have the J-type instructions where bits 25 to 0 represent the 26-bit jump address. There are two instructions. I did not list the third, typically because it is very similar to the jump instruction. So we have one where we can just jump straight to a different location in memory. For example, you can jump to the top of an assembly code, or you can jump to a function in which jump and link, once you jump to an area specified for the function, you also subsequently save the PC onto a, say maybe a return address, and then you jump to that, this is where jump register comes into play, where you jump back into where the previous location of the program counter was at.
Now, do you have a slide that, because I know we need a 32-bit address and you only show 26 bits. Do you have a slide that shows how you create the 32-bit address?
I do not.
Okay. But somehow that's done, huh?
Yeah, that's another thing that I will include into further iterations of this project. So I have some enhanced instructions. They are a subset of R-type, I-type, and J-type instruction formats. Unfortunately, due to the timing constraints, the additional enhancements have not been created. However, I do have the mandatory ones: input, output, set, interrupt, enable, and return from interrupt.
Mm-hmm.
Input and output function exactly like a load word and store word, respectively. The set IE is a set interrupt enable, where it simply just sets the, where the control unit sets the interrupt enable, so that when an interrupt request is generated, we proceed into the the states where we save the current program counter. Return from interrupt is popping the program counter and flags out from a stack. So just a little bit more on the whole interrupt sequence. There are two implementations. Both implementations jump to a specified location in instruction memory where the interrupt service routine resides. The first implementation stores the program counter in register 31 or register at return address, and upon completion of the interrupt service routine, a jump to register 31 is made to return the program counter to its previous location. The second implementation pushes the program counter and flagged register onto the stack and pops them out upon completion of the interrupt service routine.
So that's got a special instruction to return then, right? The
Yeah.
second implementation. Yeah.
Yes, the second implementation is a enhancement in
Right.
our design.
Mm-hmm.
We did not actually in the MIPS contain pushes or pops, but we can almost mimic them in a different manner.
Mm-hmm.
So the process by which the Slate X7 was created was by incremental development and delivery. Throughout the course, we started with an ALU, arithmetic logic unit for integer data types. We moved on to a dual port register file. Then we implemented the integer data path, and then we designed an instruction unit and enhanced our integer data path, and then we created the control unit and verified using assigned memory modules. Now this was delivered maybe in 2-week increments, and the whole process was just to teach us about what it's like to almost rapid prototype. So, arithmetic logic unit. This is our ALU. We have two inputs for the data, S and T, and then we have one input for the function select. These are our flags coming out of the ALU, and Y high, Y low, as I said earlier, can yield a 64-bit result. However, that really is typically only for multiply or divide. This is what we started with initially. We had these instantiations of these modules, multiply, divide, and the integer operations located in the ALU.
Mm-hmm.
A enhancement that I would like to make in the future would be to include a 4th instance of the barrel shifter, in which case, right now, the current design only allows shifting one place for shift left logical, shift right logical, and shift right arithmetic. These are some of the instructions that we have in the ALU. These allow us to complete the MIPS instructions. SP init, that is 3FC is currently where we have our stack pointer. And we do have increment 4 and decrement 4 for incrementing through our memory space. So next we moved on to a dual port register file, where we had S address, T address, D address, and D enable, in which case we can only write to the register file if and only if the D enable was asserted. It is a 32 by 32 register file, meaning it's 32-bit registers. This is the first instance of the integer data path. We started by implementing some intermediate registers, high and low. That was to test our multiply and divide functions. Overall, we just had it was mostly comprised of combinational logic, and it was tested just using memory modules, this as our top level. Then we move on to adding more intermediate registers, subsequently making our design much faster. RS and RT. RT typically, or RT was also where the data would go out into the memory. So we would, using this signal right here, we would multiplex between both data coming in or data coming from the register file.
Mm-hmm. Looks like you're getting ready for pipelining there.
Yes. which is a future enhancement I would like to pipeline in the future. However, you know, as we have these registers, there's a couple things to add, such as a forwarding unit, and overall just avoiding the hazards involved with the pipelining. So here's a block diagram for the integer data path in memory. We just tied PC in to a arbitrary value, tied the data coming in to arbitrary value in data memory. We had as a so this was a 1K by 32 data memory module, in which it had a tri-state outputs. So it either outputted impedance or the data, whether or not or if and only if these chip select and the read or write signals were asserted. Here we have the instruction unit. This also contained a 1K by 32 instruction memory. This, however, even though it has a write signal, we cannot write to instruction memory. So this is tied to 0. And we have our IR out and our sign extension coming out into the integer data path. So DT functions as the sign extended 16-bit immediate value. ALU out goes into PCN. This allows us to jump registers if we have to.
Mm-hmm.
PC out goes to PCN, in which case we can also either save memory, or we can actually again jump into another location, and then we have data memory, in which case we can if we assert the chip select and the read, we can output memory, and then we can write it to the register file.
Wasn't the PC out to PCN for the jump and link instruction? Jump and link, you needed to save the program counter to the register file, right?
Oh, yes.
That PC out to PCN.
Yes, PC out to PCN.
That's
We
right.
could save PC and then save it to the register file, or we can save it to memory,
Yeah,
restore it to memory.
got it.
Okay, so I have the top level block diagram right here. This is the completed project. CPU test is the top level module, in which case I only assert reset to test. We have data memory, input output memory. Then we have the CPU module that instantiates the instruction unit, MIPS control unit, and integer data path. So within the CPU test, we have 3 buses for address and data in for the data memory and input output memory. Now, whichever memory that is asserted depends on the chip select for either data memory or input output. But yes, so we have 3 buses for the address and 1 for the data out from the integer data path, and then 1 bus for the data memory
Mm-hmm.
and the input output. We also have the control signals coming from the MIPS control unit to assert the chip select, the write or read for both memory instances. So in the instruction unit, we have a MUX that allows us to choose between RS, which allows us to jump registers. We have a signal for jumping, and then branching, and then just loading the PC. This was a big enhancement that allowed us to, complete branching instructions and jumping instructions. And the integer data path, we have a 1-bit mux that allows us to choose between choosing the stack pointer or the S address. We have a mux here to choose between using D address or T address as the destination, or we can also use the stack pointer or the return address. Right here also is what mainly makes the enhancement possible for the interrupts. We save the flags by selecting the flags to be output into memory. We select PC in using data select to store into memory, and then we also have data out coming from RT, in which case we can also store to memory. So we have 3 different options to choose from to store to memory. And closing remarks. Future enhancements are, but are not limited to, barrel shifter, floating point, a data type, a floating point unit, and data type, and pipelining. And this class was a great learning experience for documentation and debugging.
Very good. Thank you, Oliver.